What's the most powerful explosion in the universe? Not a nuclear bomb, not even a regular supernova, but something far more violent, so immense that it can rip an entire star apart and leave absolutely nothing behind. No black hole, no neutron star, just raw energy unleashed into the void, brighter than billions of suns, powerful enough to reshape the fabric of the cosmos itself. It's an explosion so fierce that even light, the very thing that holds a star together, turns against it. Today, we're diving into that cosmic phenomenon, the pair-instability supernova, the most powerful, most complete, and most awe-inspiring act of destruction nature has ever created. So, watch this video till the end and subscribe to the channel. Let's begin. Before we can truly grasp the unimaginable fury of a pair-instability supernova, we first need to understand the scale of power that even an ordinary supernova commands. When a massive star reaches the end of its life, its core collapses and rebounds in a colossal explosion, a supernova. In that single moment, it releases more energy than our Sun will emit in its entire 10 billion year lifetime. For days or even weeks, a supernova can shine brighter than an entire galaxy containing hundreds of billions of stars. Think about that. One dying star temporarily outshining every other star in a galaxy. The blast sends shockwaves across space, hurling stellar material outward at thousands of kilometers per second, creating glowing nebulae that can persist for centuries. Even from millions of light years away, the light from these explosions can reach Earth, flashing like cosmic lighthouses in the night sky. But as mind-bendingly powerful as that is, there exists an explosion that eclipses even this titanic display. One that takes the already impossible and multiplies it beyond reason. While a regular supernova leaves behind a dense core, perhaps a neutron star, or even a black hole, the pair-instability supernova doesn't just destroy the outer layers, it annihilates the entire star. It's a runaway chain reaction so complete that nothing survives. No remnant, no trace of what once was. The power it unleashes is so staggering that for a few fleeting moments, it can pour out more energy than our Sun will generate over its entire existence. If a typical supernova is nature's greatest firework, then a pair-instability supernova is the universe's detonation of eternity, a blast that rewrites the meaning of destruction and creation all at once. The stars capable of unleashing a pair-instability supernova are unlike anything we can easily imagine, cosmic titans that defy the very limits of what a star can be. These are the true giants of the stellar world, weighing in at anywhere between 130 and 250 times the mass of our Sun. To put that into perspective, if one of these colossal stars replaced the Sun at the center of our solar system, its outer layers could extend almost to the orbit of Jupiter. Their sheer size is staggering, but it's their power and their fragility that make them so extraordinary. These massive stars burn with an intensity that dwarfs everything around them. Their surfaces blaze at tens of thousands of degrees, radiating energy millions of times greater than that of our Sun. Inside, their cores roar with nuclear fusion reactions at such extreme rates that they consume their fuel in just a few million years, a mere blink of an eye compared to the slow, steady 10 billion year life of a smaller star like ours. They live fast, burn furiously, and die spectacularly. But such stars are rare, almost vanishingly so in the present-day universe. The conditions required to form them, enormous clouds of pristine hydrogen and helium, hardly exist anymore. In today's cosmos, gas clouds are enriched with heavier elements forged by generations of earlier stars, making it difficult for gravity to pull together enough mass to create such enormous stellar bodies. That's why astronomers believe these giants were far more common in the early universe, just a few 100 million years after the Big Bang, when the first stars were born from the pure, untouched material of creation. These stellar behemoths are the engines of cosmic evolution, rare, short-lived, and utterly transformative. Each one is a ticking time bomb, destined from birth to end in the most violent and spectacular death imaginable. Their rarity only adds to their mythic status, because when one finally does reach its end, it changes everything around it, spreading elements, igniting new stars, and reshaping the future of galaxies themselves. These colossal stars, born from immense clouds of gas and dust, do not lead peaceful or measured lives like our Sun. They blaze furiously from the moment they ignite, devouring their nuclear fuel with reckless speed. Everything about them happens on fast forward: their birth, their growth, and their demise. While our Sun spends billions of years leisurely fusing hydrogen into helium, a massive star 100 or 200 times its mass completes that same process in only a few million years. In cosmic terms, that's the difference between a candle burning for an evening and a lightning strike that flares, blinds, and vanishes almost instantly. At their cores, the physics of fusion plays out on an unimaginable scale. Hydrogen atoms, squeezed together under the weight of the star's own gravity, merge to form helium. This process releases tremendous energy in the form of light and heat, which pushes outward against the crushing inward pull of gravity. It's a perfect balance for a while, but as hydrogen in the core runs out, the delicate equilibrium begins to falter. Gravity starts to win again, compressing the core until the temperature rises high enough for the next stage of fusion to begin: helium into carbon and oxygen. The star stabilizes once more, but only temporarily. This pattern repeats itself, each new stage of fusion burning hotter, faster, and shorter than the one before. Carbon fuses into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. Each stage lasts only a fraction of the time of the one before it. What took millions of years in the first phase may take only months, days, or even mere hours in the later ones. Inside, the star's structure becomes layered, like an enormous cosmic onion, with each shell representing a different element being fused. The outer layers still burn hydrogen and helium, while deeper and deeper within, more advanced fusion reactions rage, building heavier and heavier elements until the core becomes iron. Iron is where the road ends, because fusing iron doesn't release energy, it consumes it. For most stars, this is the death sentence. Once the core fills with iron, fusion stops. There's no more outward pressure to counteract gravity, and the star's immense weight causes the core to collapse in an instant. The result is a titanic explosion, a supernova, leaving behind a neutron star, or, if the star was massive enough, a black hole. But for stars in the critical mass range, those titans between 130 and 250 times the mass of the Sun, the story takes a far stranger and more violent turn before that point of iron collapse ever arrives. Deep in their blazing hearts, where temperatures reach into the billions of degrees, the usual laws of stellar physics begin to warp. These stars don't simply march toward the normal supernova path. They reach a point where light itself, the very radiation that supports the star from within, begins to behave differently. You see, radiation pressure is the star's lifeline. It's what keeps gravity from crushing the star into oblivion. In these massive stars, the outward force of light, billions upon billions of photons streaming through the core, perfectly balances the inward pull of gravity. But as the temperature keeps climbing, those photons become so energetic that they start to transform into something else entirely, and this transformation is catastrophic. Before we get there, though, it's worth reflecting on how delicate this balance is. The life of a massive star is an ongoing struggle between creation and destruction. Fusion tries to create stability, while gravity constantly tries to crush it. The star is like a dancer poised on a knife's edge. One misstep, one imbalance, and it tumbles into chaos. As the star grows older and its fuel runs out, the scales begin to tip. Gravity tightens its grip, the core contracts, and the temperature surges. Every increase in heat accelerates the reactions, making the star burn even faster, which in turn increases the heat. A self-reinforcing cycle that drives the star toward instability. What's happening inside is no gentle process. The core churns violently as convection currents of plasma transport energy outward, while turbulent waves ripple through the layers. The outer regions of the star can swell to immense proportions, millions of kilometers across, forming vast, roiling surfaces that pulse and tremble with every shift in the interior. These stars often lose enormous amounts of mass through powerful stellar winds, blasting out streams of gas and radiation that can shape their surroundings long before their final explosion. They are the ultimate examples of cosmic intensity, magnificent, unstable, and doomed. And yet, for all their volatility, they are also creators. Every stage of their burning life is a forge, producing the very elements that will one day form planets, oceans, and living things. The carbon in your body, the calcium in your bones, the iron in your blood, all were once forged in stars like these. It's as if the universe itself builds its own factories of life and then destroys them in spectacular acts of cosmic recycling. But in these ultra-massive stars, the story doesn't end in the typical way, because when the core grows too hot, when the photons inside gain enough energy to perform an act of transformation that defies common sense, the balance that has held for millions of years breaks in an instant. The star is about to betray itself. The light that once sustained it becomes the very thing that dooms it. This moment, subtle, silent, invisible from the outside, marks the beginning of one of the most extraordinary chain reactions in the universe. A process so extreme, so catastrophic, that it will not just shatter the star, but erase it completely. No remnant, no survivor. Just pure, unleashed energy spreading out into the cosmos. Deep within the blazing heart of one of these colossal stars, something extraordinary begins to unfold. A transformation so violent and alien that it defies the boundaries of everyday physics. The core, now compressed under the unimaginable weight of more than 100 solar masses, reaches temperatures exceeding 1 billion degrees Kelvin. At these blistering energies, matter behaves unlike anything we experience on Earth. Atoms are stripped entirely of their electrons, creating a dense soup of bare atomic nuclei and high-energy radiation. The core becomes a cauldron of pure plasma, a place where light and matter merge and dissolve into one another in a constant storm of subatomic chaos. Up until this point, the balance of forces inside the star, the delicate tug-of-war between gravity pulling inward and radiation pushing outward, has held firm. For millions of years, photons have been the star's lifeline. Each fusion reaction in the core releases light, and that light's pressure keeps the outer layers from collapsing. But the higher the temperature climbs, the more energetic those photons become. They no longer merely bounce around, pushing outward. They begin to collide with such ferocity that their interactions produce entirely new phenomena. The star is now operating on the edge of quantum physics, where the rules governing the behavior of light and matter start to bend. At these energies, gamma rays, the most powerful form of light, dominate the core. These are not gentle streams of illumination, but concentrated blasts of energy, each photon carrying billions of times more power than the light from our sun. Under normal conditions, they provide the radiation pressure that keeps the star stable. But as the temperature approaches the threshold of instability, these photons grow so energetic that they can no longer simply exist as light. They begin to transform. When photons become energetic enough, they can create matter, literally turning light into particles. This process is known as pair production, and it's the beginning of the end for a massive star. But even before pair production fully takes over, the star's core starts showing signs of strain. Gravity is relentless, pressing inward harder than ever, while the radiation trying to hold it back begins to falter. The structure of the star wavers, its stability hanging by a thread. From the outside, none of this is visible. The star's surface may appear calm, perhaps even beautiful, a bright blue-white sphere of incandescent fury. But beneath that surface, in the final depths of its interior, the core is entering a regime of physics that borders on the surreal. It's a world where photons can destroy themselves, where matter and antimatter appear and vanish in flashes of energy, where the equations that describe stability begin to collapse under their own contradictions. At this point, the density in the core is astonishing. Billions of kilograms packed into every cubic meter. The particles inside are colliding at near-light speeds, and the slightest change in temperature or pressure can have devastating consequences. The star is no longer a stable structure, but a ticking time bomb of quantum energy. The balance that has kept it alive for millions of years is breaking down molecule by molecule, photon by photon. It's as if the star is standing on the edge of a cosmic cliff, gravity whispering from below, and light, once its greatest ally, starting to let go of its hand. The stability of the universe's most massive creation is about to unravel, not because of an external force, but because of its own internal physics. The star's brilliance, its power, its heat, all the things that made it magnificent, now conspire against it. The fusion reactions continue at a blistering pace, releasing staggering amounts of energy, but the pressure from that radiation can no longer fully resist gravity's crushing embrace. The star begins to quiver from within. The core contracts ever so slightly, just enough to raise the temperature even higher, and that increase is fatal, because once the temperature crosses a certain line, a door opens that can never be closed again. The photons begin to transform into matter, draining away the radiation pressure that held the star aloft. This is the moment when the universe itself seems to change the rules. The laws of thermodynamics, quantum mechanics, and relativity collide inside this furnace, and the result is inevitable. The balance is broken. The core is collapsing. And as it does, the very process that sustains stars, fusion, will become the cause of their destruction. What happens next is no longer a matter of slow stellar evolution. It is a runaway event, an unstoppable chain reaction that will end not in the quiet formation of a remnant, but in the total obliteration of the star itself. The star has crossed the line between life and death, and in doing so, it has awakened one of the most extreme and rare events in the universe, a pair-instability supernova. But before the explosion comes, we must understand the strange and elegant physics behind this fatal transformation, the process of pair production, where light itself becomes matter and seals the star's fate. Deep within the collapsing core of this massive dying star, reality itself begins to twist. The heat is now beyond comprehension, billions of degrees Kelvin. Under these extreme conditions, light, something we usually think of as intangible, weightless, and eternal, begins to behave in a way that feels almost impossible. In the heart of the star, photons, the very essence of light, become so energetic that they can transform into matter itself. This is the phenomenon called pair production, and it's one of the most extraordinary yet fundamental processes in all of physics. To understand it, we have to look at light not just as a wave, but as a particle, a tiny packet of energy known as a photon. Normally, photons zip around the universe freely, bouncing off particles, fueling photosynthesis, lighting up the stars and giving us everything from sunlight to radio waves. But inside the core of a pair-instability star, photons are not just energetic, they are ferocious. Each photon carries so much energy that it can perform one of the most bizarre acts allowed by quantum mechanics. It can create matter out of pure energy. Here's how it happens. According to Einstein's famous equation, E equals mc squared, energy and mass are interchangeable. It tells us that mass is just a very dense form of energy, and energy can, under the right conditions, become mass. Inside the dying star, when two extremely high-energy gamma-ray photons collide, the energy of their impact is so great that it doesn't simply release light or heat. Instead, it materializes into two particles, an electron and its antimatter twin, a positron. An electron is familiar. It's part of every atom, one of the fundamental building blocks of matter. But a positron is something stranger. It has the same mass as an electron, but the opposite electric charge. It's the mirror reflection of matter, antimatter. When the photon's energy is converted, these two particles appear out of the blinding radiation, perfectly balanced in charge, mass, and energy. Matter and antimatter, born together from pure light. It's a stunning example of how flexible reality becomes at extreme energies. In our everyday world, light can never just turn into matter. The photons from your lamp or the sun simply don't carry enough energy for that. But in this star, the conditions are so extreme that the normal rules collapse. Every second, trillions upon trillions of these pair production events take place, filling the star's core with a swarm of electrons and positrons. But this isn't just a fascinating curiosity, it's catastrophic. Because before this transformation began, those photons were the very things holding the star up. Their radiation pressure, the outward push of light, counteracted the inward crush of gravity. Now, every time a photon turns into an electron-positron pair, that pressure weakens. The energy that once supported the star is converted into mass, and that mass doesn't provide the same stabilizing force. The core starts to lose its footing. Imagine the star's interior as a colossal tug-of-war. On one side is gravity, pulling everything inward. On the other is radiation pressure, light itself, pushing outward. For millions of years, they've been evenly matched, holding the star in delicate balance. But with pair production, one side suddenly loses strength. The photons, the champions of outward pressure, are literally vanishing, turning into particles that don't contribute to the push. Gravity, relentless and unforgiving, seizes its chance. In a heartbeat, the equilibrium collapses. The star begins to contract. The core, deprived of its internal support, starts to cave in on itself. As it does, the temperature skyrockets even higher, feeding the process that caused the instability in the first place. It's a vicious feedback loop. More collapse creates more heat, which creates more pair production, which removes more radiation pressure, leading to even faster collapse. The star is now spiraling toward destruction, and nothing can stop it. What's breathtaking about this process is how simple and how inevitable it is. It's not caused by an external force or a cosmic collision. It's a natural consequence of physics, playing out to its logical extreme. Light, which once gave the star life, now betrays it. The very photons that lifted its outer layers against gravity's pull become the seeds of its doom, transforming into matter and antimatter, eroding the stability that kept the star intact. In the blink of an eye, a stable, shining star becomes a collapsing inferno. The interior grows denser, hotter, more unstable by the second. Every moment of contraction builds up incredible tension, like a bowstring being drawn back further and further. The star's fate is sealed, and the next step will be the most violent yet. When that tension snaps, and fusion itself turns against the star in one final, all-consuming flash of energy. As the core of this colossal star descends further into chaos, the delicate balance that has kept it alive for millions of years begins to unravel in the most dramatic way imaginable. Deep within its heart, pair production, the transformation of high-energy photons into electrons and positrons, is now happening on a massive scale. This seemingly subtle shift in the behavior of light completely destroys the fragile equilibrium between radiation pressure and gravity that has held the star together for its entire life. Until this point, radiation pressure, the outward force created by the constant bombardment of photons, has been the star's only defense against gravitational collapse. Every second, countless fusion reactions inside the core released photons that streamed outward, colliding with particles and pushing back against gravity's inward pull. This tug of war defined the star's entire existence. Gravity trying to crush it, light fighting to hold it up. But as temperatures soared into the billions of degrees, the rules changed. The photons that once served as the star's shield are now betraying it, vanishing into thin air. Or rather, into pairs of matter and antimatter that no longer contribute to the star's support. The effect is immediate and catastrophic. Imagine a massive balloon held inflated by air pressure from within. Now, picture that air suddenly being siphoned away. The balloon wouldn't gently deflate. It would collapse in on itself in an instant. The same thing is happening inside the star. The outward pressure that kept it stable suddenly disappears, and gravity, unopposed, merciless, takes command. The core, deprived of its internal strength, begins to cave inward under its own colossal weight. This collapse doesn't happen slowly. It's a runaway process, a feedback loop spiraling out of control. As the core contracts, it becomes even hotter and denser, which in turn accelerates the rate of pair production. Every new burst of gamma radiation meant to fight back only hastens the disaster, because those new photons are immediately transformed into electrons and positrons, removing even more of the vital pressure needed to resist gravity. It's a vicious cycle. The hotter it gets, the faster it collapses. The faster it collapses, the hotter it gets. The laws of physics themselves seem to turn cruel. What once created balance now creates destruction. The very energy that kept the star alive becomes the mechanism of its death. In mere seconds, the core's temperature and density skyrocket beyond anything imaginable. Photons are no longer pushing outward. They are gone, consumed. The electrons and positrons they've created don't help. In fact, they make things worse. They quickly find each other and annihilate back into photons. But those photons are immediately reabsorbed and converted again, feeding the loop. The star is eating its own energy, devouring itself from the inside out. As the collapse deepens, the pressure in the core can no longer keep pace with the relentless pull of gravity. The outer layers of the star begin to fall inward too, drawn by the sudden loss of support from beneath them. For a moment, the entire star seems to implode, its interior compressing with unimaginable force. It's as if a celestial giant has taken the star in its hand and squeezed. Temperatures climb to over 3 billion degrees Kelvin. Densities increase to levels where matter behaves more like a fluid than a gas, and the nuclear furnace that once calmly produced energy now becomes a bomb waiting to ignite. But here's the cosmic irony. This very collapse, this seemingly unstoppable implosion, is what sets the stage for the most violent explosion in the universe. Because as the core compresses and heats, the fusion reactions inside it begin to accelerate uncontrollably. Elements like oxygen and silicon, which were burning in a stable rhythm just moments ago, now ignite in a frenzy of nuclear fusion. The pressure skyrockets once more, but this time it's not a gentle balance. It's a sudden, devastating release. In a fraction of a second, the core transforms from a collapsing mass into a thermonuclear bomb of unimaginable magnitude. The star has gone from being crushed by its own weight to detonating from within. All of this is the direct consequence of one simple yet profound event: photons, the most basic carriers of energy in the universe, losing their role as guardians of stability and turning into the architects of chaos. When those photons disappeared, when light itself turned traitor, the star lost its last defense. What follows will be the most extreme and final act in its existence. The collapse won't end in a black hole or a neutron star. Instead, the buildup of pressure and heat will trigger a runaway chain reaction so powerful that the entire star will be obliterated, leaving behind no remnant, no echo of its former self. The collapse, in all its fury, is only the prelude. What comes next is the universe's ultimate crescendo, the runaway reaction that will tear the star apart, atom by atom, in a single, all-consuming blast brighter than entire galaxies. The collapse happens in silence. There is no sound in space, no roar, no warning. But deep within the star, nature is screaming. The core has lost its balance, gravity has seized control, and everything begins to fall inward at a terrifying pace. As it contracts, the matter inside is crushed tighter and tighter, and the temperature skyrockets to previously unimaginable levels. What was already a nuclear furnace now becomes something far more extreme, a thermonuclear inferno, beyond anything that has ever existed since the dawn of time. Every second, gravity squeezes the core, packing its atoms closer together, forcing them into more violent collisions. The energy from these impacts drives the temperature to over 3 billion degrees Kelvin, and the pressure becomes almost infinite. Under these conditions, fusion, the process that had quietly powered the star for millions of years, suddenly loses all restraint. Instead of proceeding in a slow, steady sequence, the nuclear reactions ignite like a chain of explosives. Carbon fuses into oxygen, oxygen into silicon, and silicon into iron in an instant. The star's interior transforms into a colossal bomb, each layer feeding the next in an escalating runaway reaction. This is not an ordinary collapse. It's a self-destructive feedback loop of cosmic proportions. The more the core collapses, the hotter it gets. And the hotter it gets, the faster fusion accelerates. Each fusion event releases vast amounts of energy, but instead of stabilizing the star as it once did, this energy arrives too late to restore balance. The collapse has already gained unstoppable momentum. Gravity and fusion are now locked in a death spiral, each amplifying the other until the entire system detonates. In mere moments, the entire core becomes one single titanic reaction zone, a sphere of pure nuclear fire. To understand just how extreme this is, imagine the energy of billions of hydrogen bombs detonating simultaneously, not across a planet, but inside a single star. The rate of fusion increases exponentially, consuming the star's fuel in fractions of a second. The outer layers, still rushing inward, meet the unimaginable pressure of this explosive reaction, and what follows is beyond the limits of comprehension. The energy released by this runaway fusion is so immense that it completely reverses the collapse. The inward motion of the star is halted and then violently repelled. The core expands explosively, sending shockwaves outward at a significant fraction of the speed of light. This is not a simple blast like a normal supernova. It's a full-scale obliteration, a detonation that rips through every layer of the star and tears it apart from within. Every single atom is forced into violent reaction. Every ounce of the star's mass participates in its own destruction. For a few fleeting moments, the core is an inferno of chaos and brilliance, releasing energy at a rate that dwarfs the entire output of a galaxy. The power surging outward exceeds 10 to the 46th joules, an almost meaningless number, except to say this: it's billions of times more energy than the Sun will emit over its entire lifetime. The explosion is so complete, so devastating, that there is nothing left to hold the star together. The nuclear firestorm consumes it entirely. This thermonuclear chain reaction doesn't just end the star, it annihilates it. Unlike the core collapse supernova that leave behind neutron stars or black holes, this event leaves nothing. The entire structure is vaporized, flung into the depths of space as incandescent plasma. It's not just death, it's erasure. The identity of the star, its mass, its gravity, its light, all vanish in a single cosmic heartbeat. The energy released expands outward in a wave that travels across light years, a ripple in the cosmic fabric. For a brief instant, that dying star outshines every other star in its galaxy. The night sky, if one could witness it from a nearby world, would bloom with an intensity so fierce it would cast shadows from trillions of miles away. This is the most violent process in the known universe, an act of self-destruction so absolute that even black holes cannot compete with its immediacy. Black holes devour and compress. This explosion obliterates and disperses. It is the ultimate form of stellar death, a single, perfect moment where the universe's most powerful forces, gravity, light, and nuclear fusion, meet and destroy one another in a flash of creation and annihilation. And yet, amid this cataclysm, something astonishing happens. In that instant of total destruction, the universe creates. The overwhelming energy of the explosion doesn't just blast the star apart. It forges new elements in the crucible of its fire. Iron, nickel, gold. Even the heavy elements that will one day form planets, oceans, and life itself are born in the same moment the star dies. The ultimate act of destruction becomes the ultimate act of creation. The runaway reaction is over in seconds, but its aftermath echoes for billions of years. The shockwave races across interstellar space, carrying the ashes of the dead star into the cosmic void. These ashes will someday cool, mix with other clouds of gas, and form new stars, new worlds, and perhaps even life, all from the remains of a single moment when a giant star died in fire brighter than imagination. But before we explore the beauty of what this explosion creates, we must first witness its peak, the moment of detonation itself, when the universe's most powerful explosion reaches its full, apocalyptic brilliance and erases a star from existence. The moment of detonation is pure cosmic annihilation, the instant when nature's most extreme forces finally break free. Deep in the heart of the star, where the collapse had once drawn everything inward, the runaway fusion reactions now release a flood of energy so immense that the core doesn't merely rebound, it erupts. The pressure and temperature spike in a single blinding instant, and the star explodes outward in one all-encompassing pulse of fury. There is no sequence, no gradual unfolding, just a flash of total destruction that consumes the star in its entirety. The blast wave tears through the star's layers faster than thought, faster than anything can resist. The outer shells are hurled into space at thousands of kilometers per second, shredding everything in their path. The core, the dense burning heart that once anchored the star, is completely vaporized. The sheer magnitude of the release is beyond comprehension. Within seconds, the star's entire mass is converted into raw, unrestrained energy. Unlike a typical supernova, which collapses inward before leaving behind a remnant, a dense neutron star, or a black hole, this explosion leaves nothing behind. No compact object, no gravitational echo, not even a corpse for the cosmos to mourn. The core does not survive its own fury. It is utterly consumed by the thermonuclear chain reaction it unleashed. In the end, Even gravity's dominion is overpowered. The forces that once tried to crush the star into a black hole are instead obliterated in the fireball's ferocity. The star ceases to exist in any physical form. If you could witness this event from a safe distance, say a few million light years away, it would look like a sudden, impossible flare in the sky. A single point of light brighter than an entire galaxy, burning for days or weeks before fading back into darkness. No supernova remnant would remain. No glowing nebula would persist as a monument. The star's material is blown so far and wide, so completely scattered, that it leaves only a whisper of its existence in the surrounding space, expanding gas so diffuse that over time it becomes indistinguishable from the cosmic background. For the briefest of moments, the explosion transforms matter into pure radiance. It's the ultimate fulfillment of Einstein's equation, E equals mc squared, played out on the grandest stage imaginable. Every gram of the star's mass becomes energy, flung outward in a wave that can travel for billions of years. The luminosity reaches heights that stagger the imagination, so bright that if it occurred in a nearby galaxy, it could cast shadows on Earth, even across vast cosmic distances. There is a haunting beauty in this absolute destruction. The star's life, its billions of years of fusion, its constant fight against gravity, all culminate in one perfect moment of release. There is no remnant, no dark legacy of collapse, only pure transformation. It is as though the universe itself takes back everything it lent, reclaiming the matter, the energy, and the light in one final act of cosmic equilibrium. The silence that follows is profound. After the blinding brilliance fades, space reclaims its calm. The radiation from the explosion continues to travel outward, carrying with it the signature of the event, the light curves, the spectral fingerprints of the elements created in the blast. This is all that remains to tell the story. A faint echo that scientists, billions of years later, can read to reconstruct what happened. The pair-instability supernova stands apart from all other explosions because of this totality. It doesn't just end a star's life, it erases it from existence. Even black holes, those cosmic grave markers of massive stars, are denied here. The explosion is so thorough, so absolute, that not a single atom remains bound by gravity. Every piece of the star is thrust into the interstellar void, where it will drift and cool, becoming part of the raw material for the next generation of stars, planets, and perhaps even life. The universe, in its strange poetry, turns death into genesis. The star dies not with remnants or ruins, but with creation in its wake, a spray of elements that will someday seed new worlds. In this one impossible instant of destruction, the cosmos performs its grandest alchemy, transforming one brilliant life into the ingredients for countless others. And while this moment marks the total obliteration of a single star, it also marks the beginning of something larger. Because the energy released, the light, the radiation, and the newly forged elements will ripple outward, shaping the galaxies, the planets, and the very matter from which future beings will arise. To truly grasp the scale of this transformation, we must try to quantify it, to measure, as best as human understanding allows, the staggering energy unleashed when a pair-instability supernova tears itself apart. When the star finally detonates, the sheer power of the explosion transcends everything we understand about energy. The amount released in a single pair-instability supernova is not just immense, it's almost beyond the limits of imagination. In physical terms, the total energy output of such an event can reach up to 10 to the power of 46 joules. That's a number so vast it's difficult to comprehend. Written out, it's a 1 followed by 46 zeros, a figure that dwarfs every other natural explosion known in the universe. To grasp what that truly means, we have to compare it to something familiar. Our Sun, burning steadily in the calm vacuum of space, releases about 3.8 times 10 to the 26th joules of energy every second. Over the course of an entire year, that's around 1.2 times 10 to the power of 34 joules. That's an amount so large it could power every machine ever built by humanity for more than 10 trillion centuries. Yet it's nothing compared to the violence of a pair-instability supernova. When one of these titanic explosions occurs, it can unleash energy equivalent to billions of years of solar output, all in a single, blinding instant. Think about that. The Sun would have to burn for 1 billion lifetimes to equal the energy a dying giant releases in seconds. Even a typical core collapse supernova, already one of the most violent events in the cosmos, only produces about 10 to the power of 44 joules of energy. That's 100 times less than the most extreme pair-instability supernova. These are not just bigger explosions. They're explosions on a different plane of existence. If a regular supernova is the roar of a collapsing star, then a pair-instability supernova is the scream of creation itself, a detonation so powerful that it temporarily dominates its galaxy. For days or weeks, the light from this single event can outshine 100 billion stars combined. Telescopes from across the universe could spot it as a point of light that appears suddenly and vanishes slowly, radiating with an intensity that challenges the limits of what space can endure. At the peak of its brightness, the luminosity of a pair-instability supernova can exceed 10 to the 11th times the output of our Sun. To put it another way, if you could somehow stand far enough away to survive, the explosion would appear brighter than the full moon, even from a distance of millions of light years. It's a burst so immense that it can briefly rival the entire output of a galaxy like the Milky Way. But the power of this explosion is not just in its brightness, it's in what it does to matter itself. The core of the star, once a stable nuclear forge, is torn apart by this energy. The shockwave that follows obliterates every layer of the star and sends it racing into the void at thousands of kilometers per second. The blast expands outward, carrying with it a storm of atomic debris and radiation that will travel for centuries. The energy is so extreme that it reshapes the surrounding space, compressing and heating nearby gas clouds, sometimes even triggering the birth of new stars. When scientists model these events using supercomputers, the numbers strain the edges of simulation. The explosion's total energy output, 10 to the power of 46 joules, is equivalent to about 10 to the power of 30 megatons of TNT. For comparison, the largest nuclear bomb ever detonated by humans, the Tsar Bomba, released about 50 megatons of TNT. That means this single supernova is as powerful as 20 octillion Tsar Bombas going off at once. 20 billion trillion of the most powerful weapons ever conceived, all detonating in perfect unison. Even the idea of such force challenges our perception of reality. At this scale, energy stops being something we can measure by human experience. It's energy that warps matter, space, and time itself. It's a force capable of erasing the very structure of a star, of converting mass directly into light and radiation at an efficiency far beyond what even the most advanced fusion reactors could dream of achieving. And yet, despite this terrifying violence, there is a strange harmony in the destruction, because that flood of energy does more than destroy, it creates. Inside the inferno, atomic nuclei are smashed together with such ferocity that new elements are born: iron, nickel, cobalt, and even traces of gold and uranium. These elements are hurled into the interstellar void, where they will someday become part of new solar systems, planets, and living beings. The power that annihilates also seeds creation, spreading the raw ingredients of life across the cosmos. For a few moments, the explosion defines its corner of the universe. Its light travels outward, crossing millions of light years, carrying the story of its death to distant galaxies. Even billions of years later, astronomers might detect its faint echo, a spectral fingerprint etched into the light of ancient stars that formed from its ashes. So yes, the numbers are unimaginable. 10 to the 46th power joules, billions of times our sun's yearly energy output, hundreds of times stronger than the fiercest known supernova. But more profound than the number itself is what it represents: the universe's ability to wield power so total that it transcends both destruction and creation. This explosion isn't just a flash of energy, it's the universe resetting the table, redistributing its matter and energy for the next act of cosmic evolution. And as the last waves of energy spread outward, cooling and fading into the emptiness, what remains of that unimaginable force will linger in the elements it forged: the heavy metals, the minerals, the building blocks of worlds yet to form. The power of that single explosion lives on in every rock, every ocean, and every living thing that will someday trace its lineage back to that single moment of light. But to understand the true beauty in this devastation, we must look closer at what the explosion creates, how it forges the elements that make up everything around us, and how from a single act of obliteration, the universe begins the quiet work of creation. In the wake of the explosion, where just moments ago, a star's heart had burned itself into oblivion, something miraculous begins to unfold, a paradox of cosmic proportions. Out of complete destruction comes creation. The energy released in a pair-instability supernova is not just an act of erasure, it's a furnace of transformation, a crucible that gives birth to the very elements that make up the universe, and, eventually, us. Inside that roaring fireball, as the collapsing core tears itself apart, atomic nuclei are smashed together in an uncontrolled frenzy. The temperatures now reach tens of billions of degrees, and under such ferocious conditions, ordinary matter is forced into new forms. Elements lighter than iron, carbon, oxygen, neon, magnesium, are fused into heavier and heavier ones. Nickel, cobalt, iron, and even trace amounts of gold and platinum are forged in this inferno, born in the span of seconds. These reactions are not gentle or orderly, they are chaotic, violent, and exquisitely efficient. In a brief cosmic instant, the star manufactures more heavy elements than countless generations of ordinary stars could produce. To understand the magnitude of this process, imagine the star as a cosmic alchemist, transmuting its entire body into treasure. A single pair-instability supernova can create tens of solar masses of nickel-56, a radioactive isotope that decays into cobalt and eventually into stable iron. This decay process is what powers the fading glow of the supernova's aftermath, the lingering light that continues to shine long after the initial explosion has passed. Each glowing remnant you might see through a telescope is, in truth, the dying heartbeat of radioactive matter, still releasing energy as it transforms into new, stable elements. But nickel and iron are only the beginning. Within the most intense zones of the explosion, where temperatures and neutron densities are at their peak, even heavier elements are forged through processes known as nucleosynthesis. In this environment, nuclei capture neutrons faster than they can decay, creating isotopes of increasing mass, the seeds of gold, silver, and uranium. Though these heavier elements are produced in smaller quantities than iron, they carry immense significance. Every atom of gold that will one day glitter in a planet's crust or form the jewelry on a human wrist traces its lineage back to these final, impossible moments in a dying star's core. What follows the blast is a breathtaking ballet of cosmic chemistry. The explosion hurls this newly minted matter into space at thousands of kilometers per second, scattering it across light years of empty void. As the hot gas expands, it cools, and the heavy elements begin to condense into dust, the fine grains that will drift through galaxies, mixing with clouds of hydrogen and helium. Over millions of years, gravity will gather these enriched clouds into new stars, and around those stars, planets will form. Those planets will inherit the elements forged in that ancient, obliterated star. The iron in their cores, the oxygen in their atmospheres, the carbon that will form the basis of life. This is the profound secret of stellar death. We are the legacy of explosions. Every atom in your body, heavier than hydrogen and helium, the calcium in your bones, the iron in your blood, the oxygen you breathe, was forged in a star that died long before the sun was born. The universe, in its vastness, is an eternal cycle of creation through destruction. Stars live, burn, and die, and in their deaths, they sow the seeds of new worlds and new life. Pair-instability supernovae play a special role in this cosmic story. Because they obliterate themselves completely, ejecting all of their matter into space, they are among the most generous donors to the universe's chemical richness. Unlike stars that collapse into black holes and lock their heavy elements away forever, these titans leave nothing behind. Every atom of their being becomes part of the cosmic inheritance, a gift of matter scattered across the galaxies. Without such explosions, the early universe would have remained a simple place, filled with only hydrogen, helium, and traces of lithium. It is through the deaths of these ancient giants that the universe evolved complexity, diversity, and, eventually, the possibility of life. Astronomers studying distant galaxies have found the fingerprints of these explosions written in the spectra of ancient stars. Unusually high concentrations of iron and nickel, the telltale signs of pair-instability events that occurred billions of years ago. These chemical traces are like the signatures of long-dead giants, still echoing across time. Each one tells a story of a universe that, even in its violence, was already shaping the building blocks of everything to come. In the end, this is the paradox of power on the cosmic scale. The most destructive events in the universe are also the most creative. The fire that annihilates a star also gives birth to the ingredients of life. It's almost poetic, the ashes of a dead sun someday becoming the soil of a living world. That's the beauty hidden within the devastation of a pair-instability supernova, that from absolute obliteration comes endless renewal. And yet, for all their importance, these explosions are extraordinarily rare. The stars that can produce them are few, and the conditions that make them possible even fewer. To truly appreciate how precious these events are, and why we may never witness one nearby in our lifetime, we must understand the cosmic rarity of their origin. Across the universe, stars are born every second, hundreds, maybe thousands of them, igniting in the swirling clouds of galactic nurseries. Yet among these countless births, only an exceedingly small fraction of stars are destined for the most extreme and spectacular fate of all, the pair-instability supernova. These explosions are not just rare, they are nearly mythical cosmic events that require a perfect convergence of conditions so precise that they have become more common in the early history of the universe than in its present age. To understand why, we need to look at what makes a star capable of such a cataclysmic death in the first place. Not every massive star can experience this phenomenon. In fact, only those that are both enormously massive and exceptionally pristine can undergo the sequence of events leading to a pair-instability supernova. These stars sit in a very narrow mass range, typically between 130 and 250 times the mass of the Sun. If a star falls below this range, it doesn't achieve the core temperatures and densities needed for pair production to trigger the runaway collapse. If it exceeds the upper limit, its immense gravity pulls it past the point of instability so quickly that it collapses directly into a black hole before an explosion can even occur. It's a razor-thin line, the cosmic equivalent of balancing on the edge of a blade. But mass alone isn't enough. The star's metallicity, a term astronomers use to describe the amount of elements heavier than hydrogen and helium in its composition, is just as critical. For a pair-instability supernova to occur, the star must have an extremely low metallicity, meaning it must be made almost entirely of the simplest elements born in the Big Bang: hydrogen and helium. These metal-poor conditions are vital because metals in a star's atmosphere can dramatically alter how it evolves. Higher metallicity leads to stronger stellar winds, which cause massive stars to lose much of their mass over time. The heavier the star's atmosphere, the more easily it sheds layers of gas into space. In contrast, low metallicity stars retain their mass much more effectively. Their stellar winds are weak, and their outer layers remain intact for millions of years, allowing their cores to grow denser and hotter than their metal-rich counterparts. This makes them ideal candidates for pair-instability supernovae. But such stars are incredibly rare today because the universe has changed dramatically since its early epochs. Billions of years ago, shortly after the Big Bang, the cosmos was still chemically simple. The first stars, known as population 3 stars, were born from clouds of pure hydrogen and helium, completely untouched by heavier elements. In that era, massive, low metallicity stars were far more common because nothing yet polluted the interstellar gas with iron, carbon, or oxygen. The early universe was a blank canvas for the creation of titanic, pristine stars hundreds of times the Sun's mass. These giants burned brightly and briefly before exploding in pair-instability supernovae that seeded the cosmos with the first heavy elements, the cosmic dust that would go on to form new generations of stars and eventually planets. Today, the universe is very different. After billions of years of stellar life and death, the gas from which new stars form has been enriched with the byproducts of countless supernovae. Every new generation of stars is born into a galaxy filled with metals, not literal metallic solids, but elements heavier than helium that astronomers categorize collectively as metals. This enrichment changes everything. Modern star-forming regions produce far fewer extremely massive stars because heavy elements allow gas clouds to cool and fragment more easily during collapse, creating many smaller stars instead of one enormous one. And even when an exceptionally massive star does form, its higher metallicity ensures that it loses a tremendous amount of mass through radiation-driven winds, disqualifying it from the delicate mass range required for a pair-instability explosion. In other words, the conditions that make these cosmic cataclysms possible have become increasingly rare with time. The early universe was a forge for such giants. The modern universe is a graveyard too heavy and too evolved to produce them easily. What once might have been a relatively common event in the first few 100 million years after the Big Bang is now an almost extinct phenomenon, a flickering echo of an era when the cosmos was young, raw, and violently creative. Even among massive stars, pair-instability supernovae demand a nearly perfect sequence of circumstances. The star must be massive enough to reach the critical temperatures where pair production begins, but not so massive that gravity overwhelms it first. It must burn long enough to develop an oxygen-rich core, but not lose too much mass before reaching that stage. And when instability begins, the chain reaction must proceed cleanly and completely, a delicate dance of physics that leaves no remnant behind. The margin for error is infinitesimally small. Because of this rarity, astronomers have long struggled to find direct evidence of a pair-instability supernova in the modern universe. Only a handful of candidates have ever been observed, and even then, most are identified through indirect means, such as the unusual brightness and longevity of their light curves or the distinct chemical fingerprints in the remnants of their host galaxies. These clues point toward events so powerful and so unique that they defy the patterns of ordinary stellar death. Computer simulations have become our primary window into understanding these elusive explosions. By recreating the extreme conditions of early cosmic history, astrophysicists can model how a low metallicity, ultramassive star evolves and dies. These simulations show that once the temperature in the core exceeds about 2 billion degrees Kelvin, pair production sets in, and the subsequent collapse and detonation release the full fury of a pair instability event. When these models are compared with real astronomical observations, especially those of superluminous supernovae, whose brightness far exceeds typical expectations, they often align beautifully, suggesting that at least some of these spectacular modern explosions are indeed descendants of the ancient process that first enriched the cosmos. Yet, for all our advances in technology and understanding, these events remain cosmic ghosts, immensely powerful, yet almost invisible across the depths of time. Most of the stars capable of experiencing pair instability supernovae lived and died more than 13 billion years ago, long before the Earth existed. Their ashes, scattered across the universe, became part of the interstellar medium from which new galaxies and solar systems eventually formed. In a profound sense, everything that exists today owes its existence, at least in part, to these ancient, rare events. So when we say that pair instability supernovae are rare, we're not just talking about scarcity. We're talking about an entire era of the universe that has passed. These explosions are the fossilized echoes of the cosmos's most creative and violent youth, when the first stars painted the darkness with light and sowed the seeds of everything to come. The stars capable of producing such cataclysms were the universe's first architects. And though their kind has all but vanished, their legacy endures in every atom of heavy matter that fills the modern cosmos. The rarity of these events makes them all the more precious to science. Each time we glimpse a possible pair instability supernova in a distant galaxy, we are peering directly into the deep past, witnessing a process that helped sculpt the universe we inhabit today. And to fully understand their role in cosmic history, we must turn our attention to those very first stars, the legendary population 3 stars, the original giants of creation, whose violent deaths wrote the first chemical chapter of the cosmos. After the Big Bang, the universe was a blank canvas, vast, dark, and almost entirely empty. For hundreds of millions of years, there were no stars, no galaxies, and no planets. Space was filled only with a thin, nearly uniform fog of hydrogen and helium, the simplest and lightest elements forged in the first minutes after creation. But this emptiness wouldn't last forever. Under the slow but relentless pull of gravity, small ripples in that primordial gas began to gather, clumping together into dense pockets. These pockets became hotter and denser over millions of years until, finally, the first sparks of nuclear fusion ignited. And with that, the universe lit up for the very first time. Those first suns, born in a cosmos untouched by the byproducts of any previous stars, were unlike anything that exists today. Astronomers call them population 3 stars, the original generation of stars that marked the transition from darkness to light. They were enormous, ancient, and unimaginably bright, true cosmic pioneers. Because the early universe contained only hydrogen and helium, the gas clouds from which these stars formed were much less efficient at cooling. That meant the gas couldn't fragment into small clumps as it does today. Instead, the clouds collapsed into just a few, but incredibly massive stars, some hundreds or even thousands of times the mass of our Sun. These population 3 stars were the perfect candidates for pair-instability supernovae. Their massive sizes and low metallicities created the ideal conditions for this rare phenomenon. With virtually no heavy elements to drive strong stellar winds, these stars retained their mass throughout their short, furious lives. They burned hotter, faster, and brighter than any modern star could, achieving the precise internal conditions that make pair production possible, those critical core temperatures of billions of degrees where photons begin turning into matter-antimatter pairs. For many of these primordial titans, the end came quickly. Within just a few million years of formation, their cores reached instability, and their deaths unleashed the universe's first great explosions. These pair-instability supernovae were not quiet events confined to one corner of space. They were cosmic milestones, shaping the destiny of everything that followed. Their detonations scattered the first heavy elements, carbon, oxygen, silicon, iron, into the interstellar medium, transforming the chemistry of the cosmos forever. Before these explosions, the universe had been chemically simple. Hydrogen and helium dominated every corner, leaving the cosmic landscape sterile and inert. Afterward, the debris from those population 3 supernovae mixed with the surrounding gas, seeding it with the building blocks of complexity. The next generations of stars, called population 2 stars, formed from this enriched material. They were smaller, longer-lived, and more chemically diverse. From their ashes came the population 1 stars, the modern stars that populate galaxies today, including our own Sun. In this way, the population 3 stars acted as the universe's first forgers, shaping the raw ingredients for everything that would come later. Every atom heavier than helium owes its existence to them. The calcium in our bones, the oxygen in our lungs, the silicon in the earth beneath our feet. When we look around us, we are, quite literally, surrounded by the ashes of those first stars. Their violent deaths created the metals, minerals, and molecules that would someday form planets, oceans, and life itself. The pair-instability supernovae of the early universe were also the architects of its structure. When they exploded, they didn't just distribute elements, they stirred the cosmic soup. Their shockwaves traveled through the intergalactic medium, heating and compressing the gas in nearby regions, triggering the collapse of new clouds and the birth of new stars. In a sense, the death of one giant sparked the birth of many others. This process of enrichment and renewal became the engine of galactic evolution. However, because these events happened more than 13 billion years ago, finding direct evidence of population 3 stars or their explosions is one of the greatest challenges in modern astronomy. No such star has ever been observed directly. They lived and died long before the universe became transparent to light. What we know of them comes from computer simulations, theoretical models, and the faint chemical signatures left behind in ancient stars. Some of the oldest stars still shining in the Milky Way, stars nearly as old as the universe itself, carry traces of that first generation, containing unusually high amounts of certain elements that can only be explained by pair-instability supernovae. These ancient survivors act as messengers from a forgotten era, their chemical compositions recording the fingerprints of the first explosions. They tell us that the early universe was not a silent, static void. It was a furnace of creation, lit by colossal stars whose deaths sculpted the fabric of cosmic history. Each time astronomers analyze the light from one of these ancient, metal-poor stars, they are, in a way, listening to the echo of those first titans, hearing the whispers of their long-vanished brilliance. The population 3 stars were the giants upon whose shoulders the rest of the universe was built. Without their explosive deaths, galaxies might never have formed as we know them. The interstellar medium would have remained too pure, too thin, too simple to birth planets and life. In a poetic twist, it was destruction, those early pair-instability supernovae, that gave rise to creation. The same fire that consumed those stars gave the cosmos its diversity, complexity, and beauty. And though we may never see a population 3 star with our own eyes, their legacy is everywhere. Every atom of iron in our blood, every grain of gold mined from the earth, every molecule of oxygen we breathe is a relic of their existence. The universe as we know it is the direct heir to their violent brilliance. Yet, despite their influence, these ancient titans remain elusive, their explosions detected only through whispers of light and chemistry. To trace their existence more precisely, astronomers must look deeper into the distant universe, peering across time itself. And with the new generation of telescopes, we are finally beginning to catch faint glimpses of their handiwork, the evidence from distant galaxies that reveals the echoes of their unimaginable power. When astronomers turn their most powerful telescopes toward the depths of the cosmos, they are not just looking across vast distances, they are looking backward in time. Every faint glimmer of light from a distant galaxy carries with it a story billions of years old. Some of these lights come from the earliest stars and their cataclysmic deaths, encoded in the subtle fingerprints of their radiation. Although no population 3 star has ever been directly observed, the universe still bears their unmistakable scars, the chemical and luminous echoes of their violent ends, preserved in the light of distant galaxies and ancient stars. Detecting a pair-instability supernova directly is next to impossible today. These explosions were most common when the universe was less than 1 billion years old, a time so remote that their light has been stretched by the expansion of space into faint, red-shifted signals. Yet astronomers have learned to read those faint cosmic messages through indirect means, finding traces of these ancient titans in 2 remarkable ways: superluminous supernovae and the chemical signatures imprinted on the oldest stars. Superluminous supernovae, the brightest stellar explosions in the modern universe, are among the most promising clues. These dazzling events are dozens, sometimes hundreds, of times brighter than ordinary supernovae, and they fade much more slowly. Their light curves, the way their brightness changes over time, reveal an energy source that far exceeds what's typical for a collapsing star. When astronomers study these extraordinary outbursts, they often find that their characteristics align perfectly with theoretical predictions for pair-instability supernovae. In a pair-instability explosion, vast quantities of nickel-56 are produced, sometimes tens of solar masses worth. As this radioactive isotope decays into cobalt and then into iron, it releases an enormous amount of light, sustaining the supernova's brightness for months or even years. This is exactly what astronomers see in some superluminous supernovae, the long glowing aftermath powered not by external forces, but by the radioactive decay of heavy elements forged in the explosion itself. One famous example is SN 2007 Bi, a superluminous supernova observed in a distant, low metallicity galaxy about 1.6 billion light-years away. When its light was analyzed, astronomers found that it bore all the hallmarks of a pair-instability supernova: the right luminosity, duration, and chemical composition. It shone with a brightness 100 times greater than a typical supernova, and its spectrum revealed enormous amounts of nickel and iron. It was as if the universe had briefly opened a window back to its earliest days, allowing us to witness, in modern times, the death of a star much like the first ones that ever existed. But light alone isn't the only messenger. Even more enduring than the brilliance of these explosions are the chemical fingerprints they leave behind, signatures written into the composition of stars and galaxies that formed long after the explosion faded. When a pair-instability supernova detonates, it flings its newly forged elements into space, enriching the surrounding gas clouds with a unique pattern of metals. Later, when new stars form from this material, they inherit that pattern, locking it into their atmospheres like a genetic code. Billions of years later, astronomers can study those stars and read that code, uncovering the history of the first explosions. These chemical fingerprints are distinctive. Pair-instability supernovae produce large quantities of elements like oxygen, silicon, and iron, but very little of the heavier, neutron-rich elements like barium or europium, which are common in other types of supernovae. When astronomers analyze the light from extremely ancient, metal-poor stars in the Milky Way's halo, stars that may have formed only a few 100 million years after the Big Bang, they sometimes find precisely this pattern. Such stars contain unusually high ratios of certain elements, matching the predictions for enrichment by pair-instability supernovae. In 2014, for instance, scientists studying one of the oldest known stars in our galaxy, SMSSJ 03-1300.36-670839.3, located in the Milky Way's outer halo, discovered that it contained almost no iron, but unusually high levels of lighter elements like carbon and magnesium. Its composition suggested that it had formed from gas enriched by a single, massive population 3 star that died in a pair-instability explosion more than 13 billion years ago. The star itself became a living fossil, a direct descendant of the first stellar generation, carrying within its chemistry the story of the universe's earliest acts of creation and destruction. In more distant galaxies, astronomers detect similar clues using advanced instruments like the James Webb Space Telescope, JWST. JWST's infrared vision allows it to peer back farther in time than any telescope before it, observing galaxies that formed less than 400 million years after the Big Bang. Within some of these galaxies, astronomers have detected chemical abundances and light patterns consistent with the aftermath of pair-instability supernovae. These are not just ordinary stellar explosions. They are the fingerprints of the universe's first giants, frozen in time at the dawn of cosmic history. Even now, researchers continue to uncover faint signals that may be remnants of those ancient detonations. The diffuse glow of certain distant galaxies, the unexpectedly high presence of elements like iron and oxygen in early quasars, and the spectral imprints in high redshift observations all hint at a universe once dominated by monstrous stars that burned and died in magnificent isolation. Every discovery adds another piece to the puzzle, painting a clearer picture of how the first stars lived, died, and reshaped the cosmos. In a sense, the universe itself is an archive, and light is its librarian. The photons from these explosions have traveled billions of years to reach us, stretched and softened by time, yet still carrying their message, that once, in the darkness of the early universe, stars so vast and bright existed that their deaths changed everything. Each superluminous supernova we detect, each ancient, metal-poor star we study, is a message in a bottle from the cosmic ocean's earliest waves. But as awe-inspiring as these observations are, our understanding of them continues to deepen through the power of human ingenuity, through computer simulations and stellar models that allow us to replay the birth and death of these ancient giants, step by step, revealing in vivid detail how the pair-instability supernova shaped galaxies, elements, and ultimately, the evolution of the universe itself. To truly understand something as cataclysmic and remote as a pair-instability supernova, Astronomers cannot rely solely on observation. After all, no telescope can witness these events, as they originally occurred more than 13 billion years ago. Instead, scientists turn to the most powerful tools humanity has ever built for exploring the unseen: computer simulations. Through them, we can resurrect the first stars, watch their lives unfold in the silence of virtual space, and witness their final, explosive moments in detail that even nature itself would take billions of years to replay. These simulations are not simple animations or approximations. They are immense mathematical universes, digital laboratories governed by the same physical laws that rule the real cosmos. Within them, astrophysicists recreate entire galaxies, modeling the interactions between gravity, nuclear fusion, radiation, and turbulence over millions of years. Each simulated atom, photon, and particle of gas is tracked through equations derived from Einstein's general relativity and the quantum mechanics that governs atomic structure. It is through this marriage of mathematics and computation that scientists can observe what our telescopes cannot yet see. To simulate a pair-instability supernova, researchers start by building a virtual star. They begin with the simplest of ingredients, hydrogen and helium, just as the universe had after the Big Bang. They assign it an initial mass, say 200 times that of the Sun, and then let physics take over. The computer tracks how gravity pulls the gas inward while fusion in the core pushes outward, creating a dynamic equilibrium. As the star ages, the simulation follows each stage of its evolution: the burning of hydrogen into helium, helium into carbon, carbon into oxygen, and beyond. Layer by layer, like an onion, the star develops its stratified structure, each shell fusing heavier elements until the core reaches the critical conditions for instability. Then comes the moment of truth. When the temperature inside the star's heart exceeds a few billion degrees, the photons become so energetic that they begin to transform into electron-positron pairs. The simulation captures this in exquisite precision. Watching as the star's radiation pressure collapses, its core contracts, and its density spikes. In just fractions of a second, the virtual star experiences the same runaway fusion chain reaction that a real one would. The result, every time, is breathtaking. The star's internal structure disintegrates in an explosion that releases energy on the order of 10 to the power of 46 joules, blowing it apart completely. What makes these simulations so astonishing is not just the ability to reproduce the explosion, but to see its consequences. When the star detonates, the surrounding space fills with expanding shells of hot plasma and heavy elements. The models show how these shockwaves travel through the interstellar medium, compressing gas clouds, igniting new star formation, and enriching the galaxy with metals. In this way, pair-instability supernovae are shown to be not merely destructive, but profoundly creative, engines that drive the chemical and structural evolution of galaxies. Modern computational models have revealed that one pair-instability supernova can inject enough energy into its environment to disrupt the entire formation of a small galaxy. In the early universe, when galaxies were smaller and more fragile, a single explosion could blow away much of the surrounding gas, temporarily halting star formation. Yet as that gas cooled and fell back in, it carried with it the heavy elements created by the explosion, allowing future generations of stars to form more complexly. In this sense, each explosion was a cosmic gardener, pruning and reseeding the early galaxies, ensuring that they grew in cycles of destruction and renewal. Some of the most sophisticated models, like those run on supercomputers such as NASA's Pleiades, DOE's Summit, or Japan's Fugaku, simulate not just one star, but entire populations of them, evolving across cosmic time. These vast simulations, spanning thousands of light years and millions of years, show how the first stars and their explosive deaths shaped the large-scale structure of the universe. When the results are rendered visually, we see galaxies forming like glowing webs of light, each filament seeded by the debris of stars long dead. At the heart of those models are the pair-instability supernovae, detonating like cosmic beacons, their shock waves merging and colliding to sculpt the galaxies we see today. Simulations also allow scientists to test alternate histories of the universe. What if the first stars had been less massive? What if no pair-instability supernovae had ever occurred? The answers are striking. Without these massive explosions, the universe would have evolved far more slowly. Galaxies would have remained small and metal-poor for eons, and the conditions necessary for planet formation, and eventually life, might have taken far longer to emerge. The fingerprints of these early explosions are embedded in the very fabric of cosmic evolution. In recent years, models have become increasingly sophisticated, incorporating not just stellar physics, but also radiative transfer, hydrodynamics, and even cosmic magnetism. This allows researchers to trace how the light from pair-instability supernovae might appear to telescopes like the James Webb Space Telescope, JWST, or the upcoming Vera C. Rubin Observatory, LSST. By comparing these simulated light curves and spectra to real astronomical observations, scientists can identify potential candidates for these ancient explosions, a kind of forensic astronomy where the simulation provides the blueprint for discovery. These digital experiments also uncover fascinating subtleties about the explosions themselves. For example, they reveal that not all pair-instability supernovae are identical. Some may occur in slightly less massive stars that don't destroy themselves completely, instead undergoing pulsational pair-instability, where the star repeatedly ejects huge amounts of material in violent bursts before finally collapsing. Others might leave unique chemical signatures in their remnants, explaining why certain ancient stars have peculiar abundance patterns that can only be produced by this mechanism. In essence, simulations have become our cosmic time machines. They let us watch the universe grow from simplicity to complexity, showing how these long-vanished stars shaped the destiny of galaxies, planets, and life itself. Every new model adds another layer of understanding, refining our knowledge of how matter recycles itself across billions of years, how one generation of stars dies to give birth to the next. Through these virtual windows into the past, scientists can now see the grand design of the cosmos more clearly than ever before. They can watch the first light ignite, see the first explosions ripple through primordial gas, and follow the chain of creation that leads, ultimately, to us. The simulations tell a story both epic and intimate, that the atoms in our bodies, the dust in our skies, the iron in our blood, all are echoes of stars that once existed only in these ancient, simulated fires. And yet, even in this age of powerful computation, there remains much to learn. The pair-instability supernova, despite its simulated clarity, continues to defy easy comparison with the other known kinds of stellar explosions. To truly appreciate its uniqueness, we must contrast it with its more familiar cousins, the core collapse and type Ia supernovae, and see why, among all the ways a star can die, this one stands alone as the most complete and uncompromising act of destruction in the cosmos. When we talk about stars dying, it's easy to think that all supernovae are essentially the same: immense explosions, blindingly bright, and devastatingly powerful. But not all stellar deaths are created equal. In fact, most supernovae, as violent as they are really acts of transformation rather than obliteration. They destroy, yes, But they also leave behind something, a remnant, a dense core, a kind of stellar ghost lingering in the cosmic aftermath. A pair-instability supernova, however, belongs to an entirely different category. It is the universe's one true act of total erasure, a cosmic event that leaves nothing behind but light and expanding debris. To understand what makes it so unique, we must first look at the other main types of stellar explosions, the core collapse supernovae and the type Ia supernovae, and then see how the pair instability event breaks the pattern, taking destruction to its most absolute form. Let's start with the core collapse supernova, the more common death of a massive star. When a typical giant star, say between 8 and 40 times the mass of the Sun, reaches the end of its nuclear fuel, it can no longer support itself against gravity. The outer layers fall inward at tremendous speed, crushing the core until the pressure becomes almost infinite. In that moment, protons and electrons are forced together, forming neutrons and releasing a flood of neutrinos, ghostly particles that carry away a staggering amount of energy. The core collapses to the size of a city and then rebounds, sending a shockwave outward that rips the star apart. The result is a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. In even more massive cases, the collapse goes further, and nothing, not even light, can escape. The star becomes a black hole, a point of infinite density and gravity's final victory. These remnants, neutron stars and black holes, are the corpses of stars, silent markers of their former glory. They endure for eons, influencing the galaxies around them, devouring matter, and sometimes even merging in bursts of gravitational waves that ripple across the universe. Then there are Type I supernovae, a very different kind of explosion. These occur not in massive stars, but in white dwarfs, the smouldering remains of smaller stars like our Sun. When a white dwarf orbits close to another star, it can begin stealing matter from its companion. As it grows in mass, it approaches a critical limit, about 1.4 times the mass of the Sun, known as the Chandrasekhar limit. Beyond this point, the pressure that supports the star's structure collapses, triggering a runaway fusion reaction. Carbon and oxygen ignite explosively, and in an instant, the entire white dwarf is incinerated. Unlike a core collapse supernova, a Type Ia leaves no remnant behind. But its mechanism is fundamentally different from a pair instability event. It's not the result of pair production or the catastrophic breakdown of radiation pressure. It's a thermonuclear detonation of degenerate matter, ignited by mass transfer. Type I supernovae are relatively uniform in brightness, which is why astronomers use them as standard candles to measure cosmic distances. But while they, too, are total in their destruction, they lack the staggering scale of energy, mass, and elemental creation that defines a pair instability explosion. Now, imagine a star far more massive than either of these cases. A star so immense that its very physics begins to defy the universe's usual order. When such a star dies in a pair instability supernova, it doesn't leave behind a neutron star or a black hole. There is no dense core left to mark its death. Instead, the entire star, all hundreds of solar masses of it, is annihilated in one unimaginable detonation. Every atom of the star's core participates in the explosion. No remnant remains. In the case of core collapse supernovae, the explosion is driven by the rebound of infalling material against the newly formed neutron star. But in a pair instability supernova, the explosion comes from within, from a runaway nuclear reaction so powerful that it tears the star apart before gravity can reclaim it. Once the chain reaction begins, there is no stopping it. The star's core fuses its remaining fuel, mostly oxygen and silicon, in a fraction of a second, releasing enough energy to completely overcome its own gravitational binding force. The result is not a collapse, but a total disassembly. The contrast is almost poetic. In a core collapse supernova, gravity wins first and is later defied. In a pair-instability supernova, gravity loses outright, overwhelmed by the fury of nuclear fire. In a Type Io supernova, an old, degenerate star explodes quietly by cosmic standards, a kind of elegant self-destruction. But in a pair-instability event, the universe itself seems to erupt, turning matter into energy with terrifying efficiency. If you could witness all three types side by side, their differences would be staggering. A core collapse supernova would appear as a brief, bright flash, followed by the faint glow of a neutron star or the invisible gravity of a black hole. A Type Io supernova would blaze uniformly and then fade, leaving behind an empty space where a white dwarf once was. But a pair-instability supernova, that would be something else entirely. For weeks, it would outshine an entire galaxy, radiating billions of times more energy than the Sun will produce in its lifetime. Then it would fade, leaving no trace, no remnant, no evidence that the star had ever existed, except for the cloud of newly forged elements expanding outward to seed the future. Even its spectral signature sets it apart. Core collapse and Type Ia supernovae produce distinct patterns of elements that astronomers can identify in their light. But a pair-instability supernova reveals an excess of nickel, iron, and other heavy elements, far more than any other kind of explosion can produce. It is the ultimate foundry, turning nearly all of its mass into new matter before dispersing it across the cosmos. In many ways, this makes the pair-instability supernova the most paradoxical of all cosmic events. It is both the most destructive and the most creative, a total annihilation that leaves behind the raw material for new worlds. Where core collapse and Type Io supernovae mark transitions, the pair-instability event marks a reset, wiping the slate clean. It doesn't just end a star's life, it ends its story, while simultaneously beginning countless others. This is why, in the grand hierarchy of stellar deaths, the pair-instability supernova stands alone. It is the purest expression of the universe's dual nature, to destroy and to create, to erase and to renew. The others leave behind ghosts, remnants that echo across time. This one leaves only light, spreading its essence into the void. And perhaps the greatest irony of all is this: these titanic stars, the largest that ever lived, are the ones that fail to make black holes. They are too powerful, too luminous, too complete in their destruction. To understand why that is, why the universe's mightiest stars end in total nothingness instead of ultimate density, we must explore the haunting mystery of the absence of a black hole at the heart of these explosions. The irony could not be deeper, nor the cosmic paradox more profound. The most massive stars in the universe, those titanic furnaces that shine brighter and die faster than anything else, are also the only ones that die without leaving behind anything at all. When most stars end their lives, gravity wins the final battle. No matter how violent the explosion, something remains. A remnant core, compressed beyond comprehension, that becomes a neutron star or a black hole. But in a pair-instability supernova, gravity is utterly defeated. The explosion is so violent, so thorough, that there isn't even a fragment left for gravity to reclaim. The entire star is obliterated, erased from existence, leaving behind only expanding clouds of gas and light that drift silently through the void. This is perhaps the ultimate irony of the cosmos. Black holes, after all, are symbols of nature's dominance, the final word in the story of stellar death, the triumph of collapse over resistance. And yet, the very stars most capable of creating them, Those with hundreds of times the mass of the Sun never do. The explosion of a pair-instability supernova is simply too powerful. It unbinds the star entirely, converting its immense mass into energy before gravity ever gets the chance to finish its work. The star dies not by collapsing inward, but by tearing itself apart from within, in one catastrophic act of self-destruction. To understand how complete this destruction is, imagine the balance of forces at play. In an ordinary massive star, gravity and nuclear pressure are locked in an eternal duel. As long as the core fuses lighter elements into heavier ones, it generates enough radiation pressure to push outward and keep gravity at bay. When fusion finally stops, the core collapses. Gravity wins, crushing the star into a singularity or neutron-rich sphere. But in a pair-instability supernova, something far stranger occurs. Long before gravity can seize control, the runaway fusion triggered by pair production releases such an overwhelming amount of energy that it reverses the collapse completely. The energy generated in those final moments is so intense, up to 10 to the power of 46 joules, enough to outshine an entire galaxy, that it exceeds the star's total gravitational binding energy by orders of magnitude. In other words, the blast is powerful enough to overcome the combined pull of every atom in the star. There is no partial collapse, no remnant core, no fallback. The explosion blasts the star apart so violently that not even a teaspoon of its material remains bound by gravity. Every atom is launched into the cosmic abyss, destined to drift and cool over eons until it becomes part of something new. This complete destruction places the pair-instability supernova in a category of its own. It is the only known natural process where a star is entirely destroyed by its own internal physics, a phenomenon where energy and mass annihilate one another in near-perfect symmetry. Even the process of black hole formation, which seems like the pinnacle of stellar death, is in a sense less dramatic. A black hole's birth is quiet. Most of its violence is hidden behind the event horizon, invisible to the universe. But the death of a pair-instability star is anything but quiet. It is the loudest possible farewell, a final cry that can be seen across billions of light years, proclaiming its end to the entire cosmos. The absence of a black hole also means that the star's story is over in an instant. There is no remnant accreting matter, no gravitational echo distorting space-time, no long-term aftermath beyond the expanding debris cloud. In every sense that matters, the star is gone, completely and permanently. What remains is its legacy, the elements it forged in its final seconds, and the light that carries its death cry across eternity. Those photons, released in that brief moment of total annihilation, travel through space for billions of years, eventually reaching our telescopes as faint traces of a life that once burned brighter than any other. Astrophysicists often describe this phenomenon as a clean death. It's not just poetic language, it's literal. A pair-instability supernova is the cleanest destruction nature allows. There's no leftover core, no black hole, no neutron star, no second act. It is an end so complete that, in the cosmic record, the star ceases to exist as a distinct entity. Its matter is dispersed, its structure dissolved, its gravitational footprint erased. Only its chemical children, the iron, nickel, oxygen, and gold scattered into the interstellar medium, remain to tell the story. And therein lies the quiet genius of the universe. In denying these titans the honor of forming black holes, nature ensures that their deaths contribute rather than consume. A black hole locks away matter forever, trapping it beyond the event horizon where no light escapes. But a pair-instability explosion gives everything back, every atom, every ounce of energy. every trace of its being returned to the cosmic ecosystem. It's as if the universe uses these rare giants as a mechanism for redistribution, a way to recycle matter on the grandest possible scale. From a philosophical standpoint, there's something deeply moving about this outcome. These most powerful stars do not leave behind tombs or monuments. Instead, they leave a legacy of creation. Their destruction becomes a kind of cosmic generosity, a giving of themselves entirely to the universe that birthed them. Their ashes spread across galaxies, becoming the seeds of new stars, new worlds, and perhaps even new life. The ultimate act of power in the cosmos, it turns out, is not the creation of a black hole, a prison of light and matter, but the total liberation of energy into the fabric of existence. Yet, this absence of a black hole also makes these events incredibly fleeting in cosmic terms. A core collapse supernova leaves behind a neutron star that may emit radiation for billions of years. A black hole endures essentially forever, silently influencing its surroundings. But a pair-instability supernova is a momentary flash, an event measured not in ages, but in instants. In that brief, magnificent pulse of light, a star ends its existence completely, yet leaves behind the elements that will build everything else. It's humbling to realize that, in a very real sense, the atoms that make up our world were spared imprisonment inside black holes, because some of the universe's earliest, most massive stars chose destruction over collapse. They burned so brightly and so violently that they defied gravity itself, returning their matter to the cosmos in one final, luminous gift. But the consequences of their absence, of their complete dissolution, ripple outward across cosmic time. These explosions didn't just enrich space with elements, they shaped the very structure of the early universe. Their energy sculpted galaxies, stirred the interstellar medium, and set the stage for the next chapters of creation. To truly grasp the scope of their influence, we must look beyond the star itself, to the cosmic impact of these events, and how the most powerful acts of destruction became the architects of everything that followed. The death of a single massive star might seem like an isolated tragedy, a fleeting moment of brilliance lost in the vastness of space. But in the early universe, the explosions of pair-instability supernovae were anything but isolated. They were cosmic architects, reshaping the landscape of existence in ways both subtle and profound. Each one of these detonations, these all-consuming bursts of light and matter, helped sculpt the galaxies, enrich the interstellar medium, and ignite the chain reaction of creation that ultimately gave rise to the universe as we know it today. In the epoch just after the birth of the first stars, roughly 100 to 500 million years after the Big Bang, the cosmos was still young, fragile, and chemically simple. Galaxies were only beginning to take shape, mere wisps of gas bound loosely by gravity. Into this delicate environment, the pair-instability supernovae of population 3 stars erupted like divine forges. Each explosion released not only unimaginable amounts of energy, but also vast quantities of heavy elements, oxygen, silicon, iron, and nickel, that had never before existed. These elements spread outward at thousands of kilometers per second, carried on expanding shockwaves that traveled across interstellar space, colliding with the pristine hydrogen and helium clouds left over from the universe's birth. This process, called chemical enrichment, was the first great act of cosmic transformation. Before these explosions, the universe contained only the simplest elements. Afterward, the interstellar medium became laced with the raw materials for complexity, the very atoms that would one day form planets, water, and life itself. It was in the ashes of these obliterated stars that the building blocks of future worlds were forged. Every molecule of oxygen you breathe, every atom of iron in your blood, every trace of calcium in your bones owes its existence to this first generation of stellar deaths. But the impact of these explosions went beyond chemistry. They fundamentally altered the structure and evolution of early galaxies. When a pair-instability supernova detonates, the energy it releases is staggering, up to 10 to the power of 46 joules, enough to temporarily overpower the gravitational pull of an entire young galaxy. This energy doesn't simply vanish, it radiates outward, heating and stirring the surrounding gas, shaping it into vast bubbles and filaments. In the small, fragile galaxies of the early universe, even a single explosion could expel most of the available gas into intergalactic space, temporarily halting star formation altogether. At first glance, this seems destructive, and it is. But it's also profoundly creative. The same shockwaves that swept away gas also compressed it in other regions, triggering the formation of new stars. The heavy elements ejected by the explosions cooled the surrounding gas more efficiently, allowing it to collapse under gravity and form stars of smaller mass, stars that would live longer and more stable lives. In this way, the pair-instability supernovae acted as both destroyers and midwives, ending one generation of stars while giving birth to the next. Without these cataclysmic detonations, galaxies might have evolved far more slowly. The early universe would have remained chemically barren for eons, with star formation limited to massive, short-lived giants that burned hot and died quickly. But the pair-instability explosions changed everything. They seeded the cosmos with metals, enabling the creation of population 2 stars, smaller, cooler, and longer-lived than their predecessors. Some of these stars, still burning today in the halos of galaxies like our Milky Way, are ancient witnesses to that formative era, their chemical compositions bearing the unmistakable imprint of those first great explosions. Computer simulations show that these events likely played a decisive role in shaping the morphology of early galaxies. The energy from multiple supernovae would carve out vast cavities in the surrounding medium, enormous glowing bubbles of hot gas. Over time, these bubbles merged and cooled, forming networks of filaments that served as the scaffolding for future star clusters. This process gave early galaxies their clumpy, irregular structure, a pattern that would eventually evolve into the grand spirals and ellipticals we see today. Even on the largest scales, the echoes of pair-instability supernovae can still be traced. The distribution of elements in intergalactic space, detected through the absorption lines in the light from distant quasars, suggests that heavy elements were already widespread just 1 billion years after the Big Bang. The only plausible explanation for this level of early enrichment is that countless massive stars died in pair-instability supernovae, flinging their matter far beyond the confines of their home galaxies. In essence, these explosions were the universe's first pollinators, scattering the seeds of matter that would one day form everything from asteroids to oceans. There's another remarkable consequence to consider. The shockwaves from these explosions may have triggered the birth of new galaxies themselves. As they plowed through space, compressing gas and dark matter, they created regions of higher density that became gravitationally unstable, collapsing under their own weight to form new galactic cores. In this way, the death of one giant star might have directly sparked the birth of an entire galaxy, a cosmic chain reaction of creation and destruction stretching across billions of years. And this isn't mere speculation. Observations of extremely distant galaxies, like those captured by the James Webb Space Telescope, JWST, reveal that many early galaxies were small, irregular, and bursting with rapid star formation. Their shapes and compositions match the predictions of models where pair-instability supernovae had recently occurred. The presence of high concentrations of elements like oxygen and magnesium, far too early in cosmic history to be explained by normal supernovae alone, points unmistakably to the role of these hyper-energetic explosions. The cosmic impact of these events cannot be overstated. They marked the transition from the universe's first, simple age to its complex, structured era. Before them, the cosmos was uniform and featureless, a smooth sea of gas and radiation. After them, it became textured, layered, and rich, with the diversity that would one day give rise to galaxies, planets, and life. In a very real sense, pair-instability supernovae were the architects of everything that followed. And while the first of these explosions occurred more than 13 billion years ago, their effects are still with us today. The Milky Way's chemical richness, the diversity of stars we observe, the very elements that make up Earth's crust, all are echoes of those long extinguished titans. Every time we look up at the night sky, every time we hold a fragment of iron or gold, we are touching the remnants of their fury. Yet, for all we've learned about their influence, one great mystery remains. Can we ever see one again? Can modern science, with its advanced telescopes and simulations, catch a pair-instability supernova in real time? A direct glimpse of the universe's most powerful explosion? That search is already underway, driven by humanity's deepest curiosity. To witness once more the light of the first giants as they turn death into creation. In the modern age of astronomy, the search for pair-instability supernova has become one of the most ambitious and thrilling quests in science. For decades, astrophysicists have theorized about these cosmic cataclysms, stars so massive that they obliterate themselves entirely. But no one has ever seen one happen in real time. We have their fingerprints, their chemical echoes, their mathematical models. Yet the ultimate goal remains elusive. To witness one with our own instruments, to capture the birth, death, and afterglow of the universe's most powerful explosion. Today, with the arrival of new generations of telescopes, most notably the James Webb Space Telescope, JWST, and the upcoming Vera C. Rubin Observatory, with its Legacy Survey of Space and Time, LSST, that dream is finally within reach. For the first time in human history, we possess the tools capable of peering far enough back in time and with enough sensitivity to potentially catch one of these rare events in action, or at least see their unmistakable remnants lighting up the young cosmos. JWST, humanity's greatest eye on the universe, was designed precisely for this kind of work. Operating in the infrared spectrum, it can see through the veil of cosmic dust and observe light that has been stretched or redshifted by the expansion of the universe. This means JWST can detect the faint glow of galaxies that formed less than 500 million years after the Big Bang. Exactly the era when population 3 stars, the likely progenitors of pair-instability supernovae, would have lived and died. When JWST stares into the depths of space, it is essentially looking across 13 billion years of history, directly into the era when the first stars burned. Astronomers expect that among the faint, distant galaxies it observes, some will bear the unmistakable chemical and light signatures of pair-instability explosions. These galaxies should appear chemically young, composed mostly of hydrogen and helium, but with surprising enrichments of oxygen, silicon, and iron, the fingerprints of early, massive supernovae. In fact, JWST has already begun to uncover tantalizing clues. In 2023 and 2024, early JWST data revealed several extremely bright supernova candidates in galaxies less than 1 billion years old. Their luminosities were extraordinary, hundreds of times brighter than typical core collapse supernovae, and their light curves lingered for months, exactly as the pair-instability models predicted. One particularly striking candidate, detected at a redshift greater than 10, meaning the light left it when the universe was under 500 million years old, showed the telltale signs of radioactive nickel decay powering its brightness, a clear hint of the enormous mass and energy involved. If confirmed, this would mean JWST has already glimpsed the afterglow of a pair-instability supernova, the death of one of the universe's first-generation stars, preserved in light that has travelled billions of years to reach us. It's as if the cosmos has sent us a postcard from its childhood, and for the first time, we're beginning to read it. But JWST is not alone in this grand hunt. On Earth, another marvel of technology is about to revolutionize our view of the dynamic universe. The Vera C. Rubin Observatory, located high in the Chilean Andes. When it begins full operations in the next few years, it will embark on the Legacy Survey of Space and Time, LSST, an unprecedented 10-year project that will image the entire southern sky every few nights, creating the most detailed time-lapse of the universe ever made. While JWST peers deep into the ancient past, LSST will be our watchful eye on the present cosmos, searching for new supernovae as they happen. Its vast field of view and extraordinary sensitivity mean it will detect millions of supernovae, including rare and ultra-bright ones that may turn out to be modern analogues of pair-instability events. Even though the conditions that created the original massive population 3 stars no longer exist, astronomers suspect that certain low metallicity galaxies, particularly those in the distant outskirts of the observable universe, may still harbour stars massive enough to undergo pair-instability explosions. When LSST detects one of these hyperluminous events, it will alert observatories worldwide. Instruments across the electromagnetic spectrum, from X-ray satellites to radio telescopes, will turn their gaze toward the event, capturing every possible detail, its brightness, its color evolution, its spectral lines. These observations, when combined with JWST's infrared vision, could finally confirm the first unambiguous detection of a true pair-instability supernova in the modern universe. Such a discovery would be monumental. It would not only confirm decades of theory, but also offer a direct glimpse into the physical processes that shaped the earliest galaxies. By studying the light from these explosions, astronomers can learn how much heavy material they produce, how much energy they inject into their surroundings, and how they influence the birth of future generations of stars. In essence, detecting one would allow us to watch cosmic history in motion, to see the universe performing the same grand dance of death and rebirth that began nearly 14 billion years ago. Even beyond James Webb Space Telescope and Large Synoptic Survey Telescope, other observatories are joining the search. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will scan wide swaths of the sky in infrared, complementing JWST's deep but narrow view. The European Extremely Large Telescope, EELT, and the 30-metre telescope, TMT, will probe faint galaxies with exquisite detail, analysing their elemental abundances and revealing whether their stars bear the chemical fingerprints of ancient pair-instability explosions. Together, this fleet of instruments will weave a complete tapestry of the cosmos, one that connects the universe's first light to its ongoing evolution. And perhaps the most poetic aspect of this search is that when we finally capture a pair-instability supernova, when we see one explode, whether it happened billions of years ago or in a distant galaxy today, we will be witnessing something profoundly familiar. The light that reaches our telescopes will contain the story of our own origins, the very elements from which we are made, shining in their moment of birth. The same kind of explosion that once seeded the galaxy with the material for life will, in its death, reveal itself to us. Astronomers often say that to study the universe is to study ourselves, and nowhere is that truer than here? When JWST, LSST, or their successors finally capture a confirmed pair-instability supernova, humanity will be staring directly into the forge that made it possible for us to exist. The death of one unimaginable star will, across time and space, illuminate the greatest truth of all, that destruction and creation are not opposites in the cosmos, but twin forces in a single, endless cycle. Yet, for all the promise of discovery and technological triumph, there is a more profound reward waiting at the end of this quest. Not just data or images, but a deeper awe. Because when we finally see one of these explosions, we will not just be observing a supernova. We will be witnessing the universe performing its most powerful act of transformation, the perfect unity of death and creation that has shaped everything we are. And that realization will carry us into the final reflection of this journey. A truth that echoes across all of space and time, that the universe's most powerful act of destruction is also its greatest act of creation. In the end, everything, every galaxy, every planet, every living thing, traces its existence back to one truth written into the fabric of the cosmos. Creation is born from destruction. The pair-instability supernova is the purest expression of that truth. A single, blinding moment where a star gives everything it has back to the universe. It dies with no remnant, no shadow, no echo of its former self, yet in doing so, it becomes eternal. Its light travels across billions of years. Its ashes become the dust of future stars, and its energy reshapes the cosmos itself. These explosions were not mere endings, they were beginnings. The first pair-instability supernovae lit up a young, dark universe and seeded it with the elements that would one day form galaxies, worlds, and life. They filled the void with the promise of everything yet to come. When we look up at the night sky, we are seeing not just stars, but the echoes of those first cosmic deaths. The fingerprints of ancient giants that burned themselves into existence so that the universe could evolve beyond simplicity. And now, billions of years later, as we build telescopes to peer deeper into the past, we are, in a way, reaching back to those moments, searching for the first sparks that led, ultimately, to us. Every photon that JWST captures, every faint trace of heavy elements in an ancient star, is a whisper from those long extinguished titans, reminding us that the universe is a cycle, not a straight line. From birth to death, from collapse to creation, everything that exists is part of that endless rhythm. If one could stand outside of time and watch it all unfold, the story of the universe would not be one of chaos and destruction, but of transformation. Stars live and die, galaxies collide and reform, and even in their violence, there is harmony. A pattern of renewal so vast and so perfect that it transcends comprehension. And at the heart of that pattern, shining brighter and dying harder than anything else, are the pair-instability supernovae, the universe's ultimate alchemists, turning light into matter, matter into energy, and energy back into light again. Their legacy is written in our blood, in our bones, in the world beneath our feet. We are, quite literally, the children of their fire, the living proof that from even the most violent deaths, something beautiful can arise. The next time we gaze into the heavens and see a star shining in the darkness, we might remember that its ancestors burned so fiercely that they created everything we know. Because in the grand design of the cosmos, the line between ending and beginning does not exist. There is only transformation, the eternal cycle of light, matter, and time. And so, we end where the universe itself began, in a single, blinding act of power that destroyed a star but built a cosmos. The universe's most powerful act of destruction is also its greatest act of creation, turning death into the building blocks of everything that exists. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.